Today I have to talk to her. I've unmuted.
You're already seeing that.
Okay. Good morning.
Good morning, madam.
Good morning, everyone.
Yes, good morning.
Okay.
Good morning to you.
It's a lady.
Okay. So I hope you can see the screen.
Yes, we can.
Okay. So we're going to start from where we stopped. Okay. And sometimes the network may not allow things to go as planned. Okay. So we expect that kind of disturbance. Okay. So last week we looked at the characteristics of operational amplifiers. Okay. So in particular, we started with the ideal characteristics of operational amplifiers. Okay. We saw that the input impedance of an ideal operational amplifier is supposed to be infinite. It has zero output impedance. It has infinite open loop gain. It has infinite bandwidth and some other characteristics, the common mode rejection and so on. Okay. Then we had started analyzing the inverting configuration of an op-amp, and we mentioned a very important characteristic, or rather feature, okay, of these op-amps, that if you have an ideal op-amp, you will see that a virtual short circuit exists between the two input terminals. That is the inverting and the non-inverting input terminals. Okay? So that we can say that the two terminals track each other in potential. So if the voltage at the inverting input terminal is some voltage, maybe 5 volts, then the voltage at the inverting will also be set to 5 volts. But we're going to use that now. Okay. So we also saw that if you want to use the op-amp to achieve some of these applications, then you have to close the loop. And how do we close the loop? We apply a resistor R2 between the input terminal and the output terminal. R2 is referred to as a feedback resistor, okay? Connecting the input and output terminals, okay? Now, in this diagram that we see, okay, we have taken all the information that about the inverting configuration, and we want to analyze it in order to derive the closed loop gain. Okay, in order to derive the closed loop gain. So what are we seeing in this diagram? We are seeing we see that we have an input VI, that's an input voltage. It is applied through a resistor R1. Okay. And R1 is connected to the inverting input terminal. Okay. Then we also note that the non-inverting input terminal is connected to ground, connected to signal ground, or if you want, you can refer to it as the earth. It has 0 volts. Okay, and our output is of course taken at terminal 3, between terminal 3 and ground. Okay. So what we want to do is to analyze this simple circuit. Okay. Okay, we can start by reviewing the virtual short circuit phenomenon. We said that because of the virtual short circuit, the two terminals appear to be connected to each other, even though, okay, we're connected to each other, even though practically they are not connected. Okay. Okay. Screen sharing has stopped. Just a moment. As the window closed. Okay, so back to where we were. Okay. So I think you can now see the screen. Okay, it is back. Okay. Yeah. So we now want to analyze this circuit in order to obtain the closed loop gain. And what is the closed loop gain? It is simply the ratio of the output voltage to input voltage. Okay, so in other words, it is V0 over V1, or here we have VI. So it's V0 over VI. So let us see how we analyze this circuit. It is very simple to analyze, provided we make the assumptions that the op-amp is ideal and therefore presents infinite input resistance or impedance. It has zero output impedance, and most importantly, it has infinite open loop gain. Later on, we'll see the effect of having a finite open loop gain. Okay, so let us follow the steps in this diagram. Okay. So step 1 is for us to realize that V voltage at the inverting, or rather voltage at the non-inverting input terminal is 0, okay, because it's connected to ground. And because of the virtual short circuit, the voltage at the inverting input terminal will also become 0. Okay, will also become 0. So that is now step 2. V1 is equal to 0. It is a virtual ground because it is not practically connected to ground. Okay. Now that we have that, we can now move to step 3, because what we want is to obtain the output V0, which will enable us to obtain the closed loop gain. Okay. So we need to determine the currents flowing through the resistors R1 and R2. So in step 3, we determine the current flowing through R1. Okay. We know the voltage at this end of R1, it is VI. Okay. We also know the voltage at the other end of R1, it is 0. Okay. So we simply apply Ohm's law here in order to determine the current I1. Okay. So I1 is simply VI minus 0 divided by R1. Okay, so that is simply how we obtain the current flowing through R1. Okay. Okay. And we know that the op-amp has infinite input impedance. That means no current enters into the input terminals. Okay? So if no current enters the input terminals, step 4 is simply telling us that zero current will enter that input terminal, and zero current will also enter the non-inverting input terminal. But we're not interested in that at the moment. Okay? So when we get to this node, okay, at the inverting input terminal, we observe that all the current that flows through R1 must also flow through R2. Okay? All the current flowing through R1 must flow through R2 because it cannot flow into the op-amp input terminals. Okay? So that the current flowing through R2 is actually I1. Okay? So we can say the current flowing through R2, denoted I2, is equal to I1, which is also equal to VI over R1. Okay? I hope that is clear. Okay? So, moving on, we want to derive the output voltage, V0. Okay? We can write a simple KCL equation, okay, for this loop between the inverting input terminal, R2, output, and ground. And then the loop closes through ground. Okay? The loop closes through ground. So alternatively, the simpler way is to say we know the voltage at this end of R2, if you follow the cursor, is 0. Okay? We know the voltage at this end, at the output end of R2, or if you like, the right side of R2 is V0. So you can write a simple equation and say 0 minus V0 should be equal to I2 times R2. Okay? Should be equal to I2 times R2. Okay? You can write it down in your notes and see that you come up with equation 6. Okay? Write it out and see that you come up with equation 6.
Okay.
Okay. So you should have come up with equation 6. Okay. Of course, you have to take Ohm's law into consideration. Okay. In other words, the direction of current flow. It flows from the inverting input terminal to the output. Okay. So when you're writing your equation, you should keep that in mind. Okay. Okay. So I think we are done with that. So if you get V naught as 0 minus Vi over R1 times R2, you can see that your V naught is simply given as minus R2 over R1 times Vi. Okay. So what is the closed loop gain? Okay. Okay. We define the closed loop gain as the ratio V naught over Vi. So it would simply become minus R2 over R1. Okay. So that is the expression for our closed loop gain.
Excuse me, madam.
Yes.
Many of our friends are waiting for you to let us in, like to let them in into the lecture.
Okay. Okay.
I
I
don't
think
bring
I've
let
let them in.
into the lecture. Okay, thank you.
Okay, you're welcome.
Thank you.
You're welcome. Okay. I don't know. Kiamufumba Dennis. Even the network is unstable. Kiamufumba. Because I let him in, but he doesn't. He has poor connectivity. Hmm? Okay. So for those who have just joined, we have derived the closed loop gain of the inverting configuration of an op-amp. Okay. What are some of the observations that we make? Okay. We see that the closed loop gain is simply the ratio of two resistances, R2 and R1. Okay, the ratio of two resistances, R2 and R1. Okay, remember that earlier on we had discussed the reason for applying feedback. Okay, we say that there are two reasons. One is for stability and the other is for accuracy. Okay, because you don't want your gain to be determined by the open loop gain all the time. Okay? So once we apply feedback, we are able to determine our gain and set it. So if we set it to R2 over R1, that is what it will be. Okay. Also, stability. The stability is a result of the negative feedback. Okay, we'll study that later on. Okay. Yes, then the other thing we need to note about our closed loop gain of the inverting configuration, you should have written this down in your notes or somewhere, or you highlight it somewhere, is that it has a minus sign. Okay. What does this imply? It simply implies that there is a signal inversion, or referred to as phase inversion. Okay. So let us take a simple example and say that if R2 over R1 is equal to 10, okay, and we apply at the input VI a sine wave signal of 1 volt peak to peak, okay, then the output V naught will also be a sine wave, but of 10 volts, because the gain is 10, so it will be 10 times 1, so it will be 10 volts peak to peak, and phase shifted by 180 degrees, okay, with respect to the input sine wave. Okay, so this is what we are referring to as the inverting configuration. Okay, because of that phase shift of 180. While one meets, when one approaches its positive peak, okay, let's put it this way. If the input approaches the positive peak, the output will approach the negative peak, okay? So let us continue. Okay. So we have already discussed some of these, including the impact of applying these two resistors, R1 and R2. Okay. This one you can read. Then we want to see the effect of the finite open loop gain, okay? We derive the expression V naught over VI equal to minus R2 over R1 with the assumption that the op-amp is ideal and has an infinite open loop gain. Okay? But practically, the op-amp does not have an infinite open loop gain. It will have an open loop gain which is large, maybe 100,000 volts per volt, okay, and so on, but not infinite. So how does this affect the closed loop gain? Okay, it is very simple. Okay, so we are saying that if we denote going to this diagram, if we denote our, okay, sorry, we want to derive the output given that the open loop gain is finite, okay? What changes? Okay. Still at the non-inverting input terminal, we have a ground. That means 0 volts is applied there. Okay. But what will be the impact on the inverting input terminal? If our open loop gain is finite, okay, we can no longer make the assumption that there is a virtual short circuit between the two terminals. Instead, we now need to derive or find an expression for the voltage at the inverting input terminal. Okay, so going back here, okay. So that is what we are doing here. You do remember from, the preliminary work where we said that the op-amp is a difference amplifier. Okay, that means V2 minus V1 is equal to V0 over VA. Okay, if you go back, okay, good enough, you should have these slides on your computer so that you can also, or wherever you can print out or have them on your computer so that you can refer to them. Okay, you can go back to the earlier slides and see that V2 minus V1 is equal to V0 over A. Okay, or we start from V0 is equal to A times V2 minus V1. Okay, so if I set V2 to 0 in that equation, you can write it down somewhere or you can do some mental work. If V2 is equal to 0 in that equation and I want V1, where V1 is the voltage at the inverting input terminal, then you see that your V1 will be equal to V0 over A. Okay, will be equal to V0 over A. So you don't need to worry about what V0 is at the moment, because what we're interested in is simply an expression. You'll see that we'll be able to collect like terms like in the previous case and obtain V0 over Vi. Okay, so the voltage at the inverting input terminal is V0 over A. Okay, going back to this circuit, which we can analyze. Sorry. Here, slide 22. Okay, so sometimes I have to stop in order to mute people. So, so at the inverting input terminal, we have a voltage of minus V0 over A. Okay, previously it was 0, but now with the finite open loop gain, that voltage is minus V0 over A. And I've already told you how to derive it, how it comes about. Okay, so we can now determine the current I1 like we did in the previous case. Okay, will simply be VI minus negative V0 over A, okay, divided by R1. You can write that down. Okay, so once you have an expression for your current I1, we again hold the assumption that no current enters the input terminal. Okay, so I1 must be equal to I2. All the current flowing through R1 will also flow through R2. Okay, so we can easily determine V0 just like we did in the previous case. Okay, you simply write out your KVL, Kirchhoff's voltage law. You know the voltage at this end of R2, and you also know the voltage at the right end of R2. So when you write that equation, okay, so network issues. So continuing, when you write that equation, you should be able to obtain the gain G, okay? Okay, so this is what we're saying. You write the equation, you have I1, so you have your V naught minus the voltage at the inverting input terminal minus the drop across your resistor. Okay? You have to keep the directions of current and voltage into consideration. Okay, you know when you have a voltage drop and when you have a voltage rise, so that you arrive at this equation. Okay, so you can substitute for I1, collect like terms, okay, and you'll obtain the gain G, okay, which is minus R2 over R1 divided by 1 plus, then in brackets, you have 1 plus R2 over R1 divided by A, okay? So that is simply the closed loop gain, which you would obtain, okay? So sometimes you may find that you are required to derive these equations, so you should be able to derive them. They're not very difficult to do. Okay. Moving on. When you look at this previous equation, there's one important thing that we want to note. Okay. What happens in this equation, as A tends to infinity, okay, as the op-amp becomes more ideal, okay, your A tending to infinity will make the denominator equal to 1, okay? So you remain with G equal to minus R2 over R1 as expected, okay? Therefore, when you want to design your op-amp circuit and you want it to be as close to the ideal conditions as possible, okay, you must choose an op-amp with a very high open loop gain, okay? But when you get to the lab work, hopefully you'll do that sometime soon, okay? You'll see that the ideal case and the practical case, or the ideal results and the practical results will not differ very much, okay? So that the effect of the finite open loop gain is not very significant, okay? Yes. So moving on, what are some of the other characteristics? You may also want to note that For the inverting configuration, which we have shown, the input resistance is R1, okay? The resistance that is connected to your source, okay, to the source VI. The other terminal characteristic is that the output resistance is 0. Okay, we have not changed anything at the output, so that resistance will always be 0. Okay, so how do we derive this input resistance? I'll give it to you as a reading assignment. Okay. Okay. You have to remember that for the terminal characteristics, your input resistance, okay, in this case is different from that. Okay, your input resistance is different from that of the op-amp. Okay, because now we are looking at it as an amplifier circuit block, okay, which consists of R1, R2, the op-amp, and their connections. Okay, so VI can be any input. It can be a sinusoid, it can be a square wave, it can even be a constant value. Okay, so we are adding VI to our amplifier. Okay, so we want to determine the input resistance of this amplifier. Okay, your input, if you can see the cursor, your input voltage would be at the left terminal of R1. That's where your input voltage is. So your input voltage in this case would simply be VI. You can write it down. And then your input current is the current flowing through R1. Okay. Okay. So you can unmute yourself and give us your comment. Musoke Simon has raised a hand.
Excuse me, madam.
Yes?
I've
Yes, I
not
can hear
understood very
you.
well why the output resistance is 0.
Why?
The output resistance is 0.
Is 0. Okay. Did you attend the class last week?
No, but I read through the slides.
You see? Okay. So does
Through the
anyone
slides.
want, is there anybody who can help? Anybody who can help to explain why he said that the output resistance is 0?
I can take him through. One of the characteristics we saw in the previous lecture about the ideal of AMP was that it has got ideally 0 input output impedance. So, and already we know that impedance is almost the resistance. So the resistance at the output of amp is ideally 0. Musoke Simon, are you satisfied?
Excuse me, madam.
Okay. He has tried, I think he just restated it, but he didn't
Excuse
explain
me.
it.
Excuse me.
Okay. Yes.
This is Len speaking.
This is who?
This is still Len speaking.
Yes. Go on, please.
One of the characteristics that we discussed last week about an ideal op amp is that it should not like draw current from what? From maybe if it was connected to a load resistance.
Okay. You're talking about input impedance, but he's asking about the output.
Excuse me?
Anybody else? Okay.
Excuse me, madam?
Yes. Anybody who
Yes.
can try?
Excuse me, madam?
Yes. Go ahead.
According to the characteristic, an ideal op amp, it doesn't draw any current, and I'm just going to write the expression for Ohm's law. Since impedance is related to resistance as V over I, if it doesn't draw any current and the current is zero, if the voltage over the zero, it means that is an infinite figure. Therefore, we expect the resistance to be infinite.
You are not audible enough. I couldn't hear you very well. I couldn't hear
I'm
you very
saying,
well.
according to the
Yes.
characteristics of amp, the op amp does not draw any current out of the source.
Okay.
And therefore, from the definition of impedance as voltage over current, therefore, if the voltage over current, if current is zero, voltage over zero will mean that is infinity. That value V over I means if I have current as zero, then for impedance becomes infinity from the definition.
Yes. I can not hear you. That last part I didn't hear. But I think you were explaining the infinite input impedance. Okay, I can see another hand here. Somebody to explain the output impedance.
Madam, since the output
Yes?
of the inverting configuration is taken at the terminals of the ideal voltage source, which is A into V2 minus V1, then the output resistance is 0.
Okay. Yes, that is what it is. Thank you. Okay. Though I also remember explaining it this way and saying that at the output, okay, the current can vary from 0 to infinity. Okay, the current can vary from 0 to infinity. Okay, while the output remains fixed at A times V2 minus V1. Okay, but okay, the only scenario which can allow that to happen for current to vary from 0 to infinity is if the op-amp has 0 output impedance. Okay, that's how I explained it. But even the explanation given by, I think it's Najemba, is also correct, that at the output we have an ideal dependent source. So because it is ideal, it has 0 impedance. Okay. Yes, I think that one now is clear. Do you still have a question on that?
No.
No. Okay. So we can continue to look at a simple example. I still see some hands raised. Musoke, are you saying something? Okay. So I'll assume that maybe you forgot the hand up. Okay. So continuing, we look at a simple example. I see Galiwango, do you have a question?
Yes, madam. What you have
Yes?
to how
Pardon, please be a bit more audible. Speak louder. I can't hear
my
you.
question is like this, madam.
Mm.
What will happen to the output when we have a resistance
Oh,
in
what
the output?
happens to on the output side? Okay. Now, when we apply
We
a
have the resistance
resistance at the output, okay, between terminal 3 and ground, is that what you're saying?
coming up and the ground. Not yet. No,
Okay.
no, no.
If we apply
The
a
resistance
resistor, you're saying a resistor between terminal 3 and ground, that resistor will
no.
essentially constitute a load. Okay. And as a load, looking into the amplifier terminals, it will simply see the dependent voltage source with 0 impedance. Okay, with 0 impedance. The load will determine the current that will flow at that output, but on the side of the op-amp, the output impedance will be 0. Okay. So I think you'll get it with time as we go on. Okay, so I think we can continue looking at this simple example, where you're asked to design an inverting amplifier, okay, an inverting amplifier with a gain of -10 and an input resistance of 100 kilo ohms. Okay. The design problem simply requires you to find values of R1 and R2. Okay, so for this simple circuit, it's simply R1 and R2. Okay, so in the solution part, we can see that we already know that the input resistance of our amplifier, Ri, is equal to R1. Okay, this therefore implies that R1 must be equal to 100 kilo ohms. Okay, then we're also given the gain. We know that the gain of the inverting configuration is -10. Okay. Do note that sometimes we'll quote the magnitude, okay, of the gain, even though it's inverting, we'll give you the magnitude. And then also we can talk about gain in decibels. Okay. Of course, if you're going to find the gain in decibels, you can't do that. You must take the magnitude. Okay. So if we know R1, we know that gain is R2 over R1 is equal to 10. We can write out this expression and can clearly see that R2 is simply equal to 10 times R1. Okay. So in this case, it will simply be equal to 1 mega ohm. Okay. So that is simply how you do a design problem. Okay. I also refer you to the problem, the design problem from the inverting configuration in microelectronic circuits. Okay. Please ensure that you look through that problem. Okay. So there are also, of course, other constraints which you can introduce. You can look at the trial exercises, and you can also look at the back of the chapter 2 of microelectronic circuits. There are many simple problems which you can attempt. Okay. Yeah. Do you have any questions? So I think Zoom wants to cut me off. Mhm. Mhm. No, that is the, I think I've stopped screen sharing. Okay. Any questions? Can be so feel free. For this one. Hmm. Hmm. So my network seems to be failing me. Okay. But I'm haven't reached yet. Eh. Okay. So I can see that you are still there. My network is having issues. Okay. Okay. So I hope you have been able to solve this simple problem. Okay. Okay. Oh. No, the next thing is the weighted summer. Weighted summer. So I think at this point, I don't know that some of you might have left because I thought the time was up. But if you are still there, I think we can continue. Okay. Okay. So if you're still there, I think we can do a little bit more. Hopefully it will not cut off without my knowledge. Okay, so anyhow, we have looked at the inverting configuration. The next thing is looking at the weighted summer. Okay, this is simply an application which utilizes the inverting configuration. Of course, later on we'll look at the non-inverting as well, and we can also replicate these applications with the non-inverting configuration. But let us start with the inverting, which is simple. So what is the weighted summer? With the weighted summer, we simply have a number of inputs. Here you can see VI applied through R1. You can see V2 applied through R2. And then various other inputs up to Vn applied through Rn. Okay, so we apply all of these to the inverting input terminal. Okay, the inverting input terminal. The analysis is basically the same. Okay, we have currents I1, I2, In flowing towards the inverting input terminal. Okay, so then of course you expect that all the current will flow through RF, since no current is admitted by the input terminals or the op-amp. Okay. So how do we analyze this circuit? It's very simple. As you can see, you simply apply KCL at the inverting input terminal. Okay, so we assume our op-amp is ideal so that 0 volts, which is at the non-inverting input terminal, is also applied or appears at the inverting input terminal. So at that point we have 0 volts. Okay, therefore I1 will simply be V1 over R1. Okay, I2 will simply be V2 over R2. And In is simply Vn over Rn. Then using Kirchhoff's current law, we can determine the current I, which flows through the feedback resistor RF. So I is simply the sum of all these currents, okay? I will be equal to I1 plus I2 all the way up to IN, okay? So you substitute, okay, for I, okay? When you write your equation for the output voltage V0, okay, for the output voltage V0, you will come up with this expression. Of course, taking the direction of current into consideration, you'll have 0 minus V0 over RF is equal to I. Okay, then you make your V0 the subject, substitute for I, and you obtain that equation. V0 is minus, in brackets, RF over R1 times VI plus RF over R2 times V2 plus plus RF over Rn times Vn. Okay, so it is essentially summing the different input voltages. Okay, and we talk about weighted summing because of the factor RF over R1, which multiplies V1, and RF over R2, which multiplies V2. Okay, that means each input voltage is, okay, modified by a weight. Okay, or a weight is applied to each input voltage, and that is why we refer to this amplifier as the weighted summer. Okay, so moving on. Okay, we have a simple problem for you to try out. It is also a design problem. Okay, you are required to design an inverting op-amp circuit to form the weighted sum V0 of two inputs, V1 and V2. It is required that V0 is equal to minus V1 plus 5 V2. Okay, so what do we have to do? What are the other constraints of the circuit? They tell us that choose values for R1, R2, and RF so that for a maximum output voltage of 10 volts, the current in the feedback resistor, will not exceed 1 milliamp. Okay. So our V0 is simply given by this equation. V0 is minus, then in brackets we have RF over R1 times V1, okay, plus RF over R2 times V2. Then when I compare this equation for the weighted summer and the equation we've been given, we can see that RF over R1 must be equal to 1, which implies that R1 is equal to RF. Okay. Also, RF over R2 is equal to 5. Therefore, R2 must be equal to RF over 5. So in this design problem, we have 3 unknowns. So when you meet such a problem, in some cases, well, in most cases, you'll set one value, and that one value will set all the other values. Okay. So we're given an extra constraint that the maximum output voltage of 10 volts, okay, while the current, the feedback resistor, okay, the maximum current that you will have in the feedback resistor is 1 milliamp, okay? So we can find an optimum value for RF, okay, to simply be 10 divided by 1 milli. So if we set our feedback resistor to 10 kilo ohms, we then obtain R1 as 10K and R2 as 2 kilo ohms. Okay. And R2 as 2 kilo ohms. So that is how you'd simply go about these design problems. Of course, the more the problems you attempt, the better you'll be at designing these OPAMPS. Okay. Then practically you'll find that you may be constrained, maybe you want to use a certain number of resistors. Okay. So you have to find a way of connecting them in parallel, in series, star, delta, okay, or whatever connection, so that you obtain a certain value, okay? Yes, so designing is sometimes challenging, but you must have an output which you want to achieve given some constraints. Okay? So that is the weighted summer. I think we should briefly look at the non-inverting. If some people left, I apologize, but some things are beyond. Okay, so the non-inverting configuration. So let me see. By show of hands, how many of you have downloaded Cedra Smith's book, Microelectronic Circuit, or you have hard copies?
Tell your kids to stop shouting for us.
So only a few people have downloaded the book. Oh, some people try to use the Mwele. No, I just gave you the link, so you can copy the link and put it in your browser. Alternatively, you type in Google microelectronic circuit, free copy, and it will give you the book. Okay, you'll be able to download it. Okay. I don't know whether the people at the photocopiers still have copies. Okay. You still acquaint yourself with those copies that are available there. Okay. Because I want to give you a quiz, hopefully when Muwele is back on board, I don't know whether they're finished whatever they're doing, I'll be able to give a quiz on OPAMPS, or maybe I'll give it at the end if we get to that, if we get that far. At the end of OPAMPS, which should be sometime next week, we should finish OPAMPS. It's a very short topic, And it is also very simple to follow and to understand. Yeah? Okay. Okay. So I encourage you to get the book and start
Excuse me,
reviewing.
madam.
Yes.
There is a quiz on Mwele, which is that it opened on 7th and closed on 16th. So how do we go about it? Should we wait? Will you adjust the date?
No, I think it is not complete, isn't it? Is it? I'll just check and see. If it is there, you do it. But Amuela has been down, so I didn't have look at it today or even yesterday. But if the quiz is there and you can do it, you do it. But I'm going to review it. But hopefully by the end, I think when we finish OPAMPS, I should give you a short quiz to really be a tester. Okay. Yeah. You're supposed to return sometime in April, isn't it? I don't know. But in the meantime, but I'll inform you. If it's a test, I'll inform you. Yeah. A test will not last 1 week. I'll give you a short time. Okay. So I think we can continue to the non-inverting configuration. Okay. And I also encourage you to draw these circuits. Okay. Because the characteristics of the circuit will remain the same, even though I change a few things, okay? So it is good practice for you to learn the different circuits and know what the output is and what the input and output terminal characteristics are, okay? Because most of the time you'll be required to either design or analyze a circuit, okay? So if you're doing analysis, you should know that this is inverting, this is non-inverting. So if you may not be as, because you may look at the circuit but not keep it in the mind. But if you draw it, then perhaps you keep it in mind. Okay? Yes. So this is the non-inverting configuration of the op-amp. Okay. Yeah. So issues of the quiz, I'll first check on Mwele and see what is there. Then I'll let you know. Okay. When it's up, I hopefully sometime this week it will be back. Okay. I was just looking at the chat messages. So anyhow, the non-inverting configuration, you should have drawn it in your book if you have a book somewhere. Okay. So with the non-inverting, let us see what it has, okay? Our input signal or input voltage VI is applied to the non-inverting input terminal, okay? This one with a plus, okay? We still have resistors R1 and R2. R1 this time is connected between the inverting input terminal and signal ground, okay? So in other words, one of its terminals is grounded while the other is connected to the inverting input terminal, okay? Then we also have R2, again applied between the inverting input terminal and the output. That means it still applies negative feedback. It still applies negative feedback, okay? So the only difference between this circuit and the inverting configuration is that now we have applied an input to the non-inverting input terminal, okay? Non-inverting input terminal. Okay, so we again want to analyze this circuit in order to obtain the closed loop gain, denoted G, which is the ratio of output voltage to input voltage. Okay. Okay. Okay, so V naught over Vi, we will show that this closed loop gain is equal to 1 plus R2 over R1. Okay. Okay, so how do we derive it? We again follow the steps. Okay. We assume that the op-amp is ideal. Okay. Is ideal with infinite input impedance, infinite open loop gain. Okay. So if we start with the terminal 1, step 1. What is step 1 telling us? VID is equal to 0 volts. That means the differential input voltage between the inverting and non-inverting input terminals is 0. Okay, that is because of the virtual short circuit. That is the differential. That's why it's VID. Okay. Now, VI is applied to the non-inverting input terminal. Okay. VI is applied to the non-inverting input terminal. Okay. Therefore, we expect that even the voltage at the inverting input terminal, at that point where the cursor is, will also be equal to VI. Okay, so VI will appear there. Okay, because of the virtual short circuit between those two input terminals. Okay, so if we know the voltage there, we can determine the current that flows through R1. Okay, we know VI, and we know that the other end of R1 is grounded. So we can write a simple expression, and also you can see the direction of flow of current, isn't it? Okay, it's flowing from the op-amp, okay, through R1 to ground. And that is why when we write our expression for the current, it is actually VI over R1. So that is step 3. Now, we know that no current is going to enter the op-amp input terminals. Therefore, all that current must flow through R2. Okay. So we have the current VI over R1 flowing through R2. Okay. We know that current, we know the voltage there, it's VI. So we can write a simple KCL equation for that loop containing R2, okay, in order to determine V0, okay. Alternatively, somebody can say, given the polarities, V0 is equal to the drop across R2 plus VI. Okay, is the drop across R2 plus VI, and that will give us this expression. Okay, V naught is equal to VI plus VI over R1 times R2. Okay, and when you write it out, okay, you get your V naught equal to VI times 1 plus R2 over R1. Okay, and our closed loop gain is simply V naught over VI. So you can write this down in your notes, that the closed loop gain G is equal to 1 plus R2 over R1. Okay, it's already given in the previous slide, but now that we have derived it, you can write it again. Okay, so that is simply the non-inverting configuration. What do we notice? Okay, again, our gain is determined by the values of passive components R2 and R1. Okay, also this gain is non-inverting. Okay, which means that the input and output will be in phase. Okay, will be in phase. Unlike the inverting configuration, where input and output are 180 degrees out of phase.
Excuse me, madam.
Okay. Yes.
Excuse me, madam.
Go on.
Like, why is the current that flows through R1 facing that direction? Like the current at 3, it's facing the opposite direction. Why?
Because you see on the right side, okay, we have a voltage VI. Okay. On the other side, we have a signal ground. So you'd expect that current will flow towards the signal ground, isn't it? That is what we expect, that current will flow through the lower, will flow towards, okay? It will flow from a higher potential to a lower potential. Okay? Yes. So that is why the direction of current is as shown. Okay?
Yes, madam.
But if VI, for instance, is negative, is a negative value,
Madam.
okay, then of course your current will flow in the opposite direction. But here we haven't put any limits on VI. We assume it is positive, okay? So current must flow from the higher potential to the lower potential, okay? Alternatively, I always give students this alternative, that you can choose to set your direction in the opposite way. Okay, so you let this current flow from the earth into R1. Okay, you'll see that you'll come up with negative values, which will imply that the current flows in the opposite direction. Okay, yes. I hope that is clear. Yeah, I think it is. Yes?
You observe the. Yes, madam.
Yes?
I'm asking that when you look at that junction and that current divide at that junction we are observing.
Yeah, yes, sir. Pardon, please.
Yeah, that one. That one. I'm saying that that current V1 out of R1 can't it divide at that junction where the capacitor is, and we obtain the case 0. whereby there is the division of current at that junction where the cursor is now.
I
If you're
can
okay with that.
hardly hear you. Are you using the Macquarie network?
Yes, I'm saying that can't we obtain current
Yes.
division
Hmm?
at that junction
This junction, okay?
where the cursor is? Can't we obtain the cursor?
Hmm? Okay.
No?
This junction, how current divides?
I'm saying that can't we obtain current division? That junction,
Current division,
yeah, where there is the cursor right now.
how would it work?
Yes, at that junction.
Current division, no, because for current division, you must have resistors in series. No, current division parallel, isn't it? Yes. So you're saying that R1 and R2 are in parallel. That's what you're saying?
Yes, I'm looking at that junction. Yes, I'm looking at that junction as if current may divide.
Yeah,
And
like
one
as though they're in
as
parallel. They are not in parallel at all, okay? Remember, what are the conditions for parallel connection? One, the two ends, of the device of the elements. If they're resistors, the two ends of the resistors must be connected at the same points. That is the first condition, which is not met here, okay? The other is that current must divide. But here, current is not dividing because no current enters the op-amp terminals. Okay? No current enters the op-amp terminal. So all the current flowing through R1 must flow through R2. Okay? The direction doesn't matter, the direction of flow. Okay, because the direction will eventually depend on the voltage VI. Okay, so they are definitely not in parallel. They are more or less in series. Okay, but because we have the op-amp there, that voltage is not determined by voltage. You say current division. Current division is for parallel connected. Okay. Yeah. Maybe you are looking at this non-inverting. You want to derive the expression using voltage division. Here it's only voltage division which can work. Okay. Because when you look at this circuit, you still have V naught there. Okay. Then R2, R1, and ground. So when you look at this circuit, it appears like as though VI is a portion of V naught. V naught, okay? You write, make VI the subject here and see what you come up with. Okay, you'll see that it appears like as though VI is a portion of V naught, implying that there's some voltage division. It looks like a voltage divider problem. Okay, so I don't know whether that's what you were talking about or not. Okay. Yes?
I've got it.
Eh? You've got it. Okay.
Yes.
Yes. So this is our non-inverting configuration. The gain G is simply 1 plus R2 over R1. Okay. Okay. So now the non-inverting characteristics, the terminal characteristics, okay. the first thing which we observe is that the closed loop gain G, who's when? Okay, the closed loop gain G is greater than or equal to 1, okay? That means the smallest gain you can get is 1, okay? The other...
Excuse me, madam.
Yes?
From the other analysis diagram,
The previous diagram?
we are seeing
Yes?
we are seeing current coming from the output toward this end. Yes, yet it is non-inverting. So I'm confused there, as if it is giving out a feedback. So can you explain
We are
more about
seeing
that
current
flow from
coming
the output
from
to this side?
the output. Okay. Yes, it is an amplifier, so it shouldn't come as, strike you as a shocking thing that the output can be larger than the input. That is not something shocking. It's an amplifier anyway. Okay. But it's just that the way our circuit has been set, okay, is such that the output is given by that expression, okay? So I think your problem is with circuit. Have you tried to redo it? Maybe you're saying that you want the current here to flow in the opposite direction. Is that what you're saying?
Yes.
Why? Because you
Yeah.
think that current cannot flow from an output? Okay. This is an amplifier. That means it can give you an output voltage which is greater than the input voltage. Okay. But also it is logical for us to show that current flows in that direction coming from R1. Okay. If you have VI, okay, at one end of R1 and you have a ground at the other end of R1, okay, you expect current to flow towards the ground, okay? It is only if you have negative voltages that you'd expect current to flow from the ground, okay? So most of the time, the current flows into the ground, okay? Not from the ground. Is that okay?
Yes.
Okay. Then I also gave you an alternative, and I said that if you want, you can denote your currents in the opposite direction, but of course, you denote them as I1 and I2, okay? And then determine I1 and I2. You'll find that they'll give you a negative value, or you'll have a negative in your expression, implying that the currents actually flow in the opposite direction. So you can do that. Huh? You try it and see what you get. Put the currents arbitrarily to flow in the opposite direction. Okay? Yeah. This one shouldn't be a big problem after. Okay? We haven't set a value for VI. We don't know whether it's positive or negative, but here we just take it as it is. That's VI, it is some positive value. Okay? Not that it's some positive value, but just taking it as it is. It has no minus. If it had a minus, then I would say maybe the current should flow in the opposite direction. Okay? Yeah. But this analysis is correct. Okay? Yeah. If you do it and get something else, then you let me know. But for sure, this one is correct. It has been known for decades. Okay. So let us go briefly. We summarize what we have looked at. Okay. we have seen that for the non-inverting configuration, the closed loop gain is greater than or equal to 1. Okay, that means the smallest value that you can get there is 1. Okay, the other thing is that it has infinite input impedance and 0 output impedance. So as part of your reading assignment, you are required, first of all, to show that the input impedance of this amplifier is infinite and that it has 0 output impedance. Okay. Also, you're required to derive the closed loop gain for the non-inverting configuration for a finite open loop gain. Okay. Finite open loop gain. Now, we have a few minutes, but I think that it is best to, I think we can stop here this time. It's almost midday, and many people have left anyway. At the peak, we were almost 70, but now there are only 50 people. On Muwele, there are about 113. Okay, I don't know how many you are in your class. Okay, and therefore how many people are actually attending. But that's not a very big problem. So the next time we meet, I think we can meet tomorrow. I think I should send out a link also so that we meet tomorrow. Oh, yeah, at 9 o'clock. Okay. I don't know how many are using the campus, whatever, but it doesn't matter. So tomorrow we'll start with the voltage. We'll look at the voltage follower, continuing with non-inverting, and we'll also look at the differentiators, and we'll look at the differentiators and the integrators, their limitations, okay? And hopefully in the coming week, we'll be able to conclude with the non-ideal characteristics. Okay, let's try to come from the current from R1 similar. So I'm looking at some of your chats. Okay, like somebody saying, just try to cram the fact that current from R1 is the same as that flowing to R2, regardless of the direction. Okay, so anyhow, so that's how he has understood the things, or she. I don't know. But anyway, thank you for attending. Do you have any questions? If I have a quiz, I'll let you know. If it's a test, I'll also let you know. I'll let you know in advance, or I'll give you enough time to do it. I always let students know. Yes, so let me check that quiz first. And then, but if it is there, you can do it. But I don't think it was complete. I'll look at it and see. But well, so try to do the assignments. If you have a notebook, you write them there. Okay, you can write them. Write all these assignments. Perhaps when you return, I may ask for the assignments. Okay, but these are really for your own work reading assignments. But I can ask you to submit them. Okay. But we'll see how we go about
Excuse
it.
me,
But they're
madam.
really reading assignment. You read and write. Okay. Some people didn't do assignment on Muwele. You'll do the other assignments as they come. Okay. So when I say it's a test, you must do it. Well, a quiz must be done. Okay, we'll have more formal assignments as we go along. Usually there will be group assignments. Okay. Yeah. So I think if we don't have any other business, we can stop here and hopefully meet tomorrow. Okay. Or we can have a 3-hour, okay, it's okay. Let's meet tomorrow and then we'll see how to go about it in the future. Okay. So thank you for attending and hopefully we'll meet tomorrow. Okay. I don't know, some of you might be having network challenges like I also do, but we'll sort them along the way. So goodbye.